Welcome to the General Chemistry 1 class. This section is Dalton's law of partial pressures. In this lesson, we will use Dalton's law of partial pressures to relate mole fraction and partial pressure of gases in a mixture. John Dalton found out that for a mixture of different gases, the pressure of the mixture is the sum of the pressure of the components as if it were alone. Consider a mixture consisting of gases 1, 2, and 3. The pressure exerted by a component gas is called partial pressure. In the illustration, P1 is the partial pressure of gas 1, P2 is the partial pressure of gas 2, and P3 is the partial pressure of gas 3. The sum of these partial pressures corresponds to the total pressure of the mixture, where P total is equal to P1 plus P2 plus P3. Using the ideal gas equation, the partial pressure of the components can be determined. Note that the temperature and volume is a constant for all components since they are all in one container at the same temperature. For gas 1, the P1 is equal to N1RT over V. For gas 2, P2 is equal to N2RT over V. And for gas 3, we have P3 is equal to N3RT over V. Getting the sum of the partial pressure is expressed in terms of the number of moles, temperature, and volume, where P total is equal to P1 plus P2 plus P3 or N1RT over V plus N2RT over V plus N3RT over V. Factoring out the constants where P total is equal to the quantity of N1 plus N2 plus N3 times RT over V, or N total times RT over V, where N total is the sum of the amount in moles of all components. The ratio of the partial pressure of the gaseous component, I to the total pressure, is equal to the mole fraction of that component. Rearranging the equation yields where Pi is equal to Ni over N times total times P total, or Ni is equal to Xi times P total, where Xi is equal to Ni over N total. Mole fraction denoted by X is the ratio of the amount in moles of a component to the total number of moles of all components. Going back to our example, the partial pressure of each component in terms of mole fractions and total pressure is given by P1 is equal to X sub 1 times P total, where P2 is equal to X2 times P total, and P3 is equal to X3 times P total. Let us solve problems about Dalton's law of partial pressures. Let us apply your knowledge. Example number 1. A 10.0 liter balloon contains 0.350 mole of helium and 0.450 mole of neon. If the gas is maintained at 20 degrees Celsius, A. What is the partial pressure of each gas in the vessel? B. What is the total pressure of the whole mixture? Given data are the number of moles of helium, where it equals to 0.350 moles, and number of moles of neon is equal to 0.450 moles, and volume is 10 liters, and temperature is 20 degrees Celsius, or it can be converted into 293.15 Kelvin. For the first question, we are asked of the partial pressure of the components, given the amount in moles, volume, and temperature. To do this, we will use the ideal gas equation in solving for the partial pressure. For the partial pressure of helium, where P is equal to nRT over V, plugging in the given data, we have P is equal to 0.350 moles times 0.0821 liter atmosphere per mole Kelvin times 293.15 divided by 10.0 liters. Simplifying, we get 0.8424 atmosphere or 0.842 atmospheres. The answer must have three significant figures based on the given values. However, we need to use a more exact answer to minimize errors in calculating the total pressure. With this, we will use 0.8424 atmospheres in calculating the final pressure instead of 0.842 atmosphere. For the partial pressure of helium, where P is equal to nRT over V, plugging in the given data where P is equal to 0.450 moles times 0.0821 liter atmosphere per mole Kelvin times 293.15 divided by 10.0 liters. Simplifying, we get 1.083 atmospheres or 1.08 atmospheres. Again, we need to use a more exact answer to minimize errors in the calculated partial pressures. With this, we will use 1.083 atmospheres in the calculation of total pressure instead of 1.08 atmospheres. To get the total pressure, simply add the partial pressures, where P total is equal to P of helium plus P of neon. Plugging in values, we have P total is equal to 0.8424 atmospheres plus 1.83 atmospheres. From the answers in the first question, only the digits covered by the red bracket are significant. Simplifying, we have P total is equal to N1. We have P total is equal to 1.9254 atmospheres or 1.93 atmospheres. Since the significant digits must not go beyond 2 decimal places based on the partial pressure values. Congratulations! You did a great job. Now let's proceed to example number 2. For example number 2, we have a 50.0 liter vessel containing or consisting of 0.400 moles of nitrogen, where 0.750 moles of argon and 0.450 moles of helium is kept at 20 degrees Celsius. A. What is the partial pressure of each gas in the vessel? B. What is the total pressure of the whole mixture? So given the data are 0.400 moles of nitrogen and 0.750 moles of argon and 0.450 moles of helium, and volume we have 50 liters and temperature of 28 degrees Celsius, or in Kelvin it has 301.15 Kelvin. To answer the first question, we will use the ideal gas equation. For the partial pressure of nitrogen, where P is equal to nRT over V, substituting the values where P of nitrogen is equal to 0.400 moles times 0.0821 liter atmosphere per mole Kelvin times 301.15 Kelvin divided by 50 liters. Simplifying, we get P of nitrogen where 0.1978 atmosphere or 0.198 atmospheres rather. For the partial pressure of argon, where P is equal to nRT over V, substituting the values P of helium is equal to 0.450 moles times 0.0821 liter atmosphere per mole Kelvin times 301.15 Kelvin divided by 50 liters, and simplifying, we get pressure of helium is equal to 0.2225 atmospheres or 0.223 atmospheres. To get the total pressures, simply add the partial pressure, where P total is equal to P of nitrogen plus P of helium plus P of argon. Substituting the values where P total is equal to 0.1978 atmosphere plus 0.3709 atmosphere plus 0.2225 atmospheres, giving 0.7912 atmospheres. From our final answers in Part A, significant digits are up to 3 decimal places, as indicated by the red brackets. Hence, the final answer is 0.791 atmospheres. Congratulations, you got good answer. Now let's proceed to example number 3. A gas tank contains 0.600 moles helium and 1.80 moles of oxygen. Given the gas mixture in the tank has a pressure of 6.00 atmospheres, what is the partial pressure of each gas in the tank? Given values are the amount of helium, where 0.600 moles, and amount of oxygen value is 1.80 moles, and the total mixture of 6 atmosphere. We need to find the partial pressure of helium and oxygen. The steps in calculating the partial pressure of a component: first, calculate the total number of moles. Second, get the mole fraction or Xi, and the third, get the partial fraction by multiplying Xi by the total pressure. To solve the problem, let us start from calculating the total number of moles. The total number of moles is equal to the mole of helium plus mole of oxygen. Substituting values where N total is equal to 0.600 moles plus 1.80 moles, giving 2.40 moles all in all. Second step. Get the mole fraction of each gas by dividing the number of mole of each gas by the total number of moles. For helium, X of helium is equal to 0.600 moles over 2.40 moles, which is equal to 0.250. For oxygen, X of oxygen is equal to 1.80 moles over 2.40 moles, which is equal to 0.750. Take note that mole fraction values are unitless quantities. To check if our mole fractions are correct, The sum of mole fractions of all components must be equal to 1.0, okay, must equal to 1. So 0.250 plus 0.750 is equal to 1. Therefore, the answers are correct. Last step. Calculate the partial pressure of each gas from the mole fraction and total pressure. For the partial pressure of helium, P of helium equals X of helium times P total. Substituting the value of P of helium equals 0.250 times 6.00 atmosphere, which is equal to 1.50 atmosphere. For the partial pressure of oxygen, we have P of oxygen equals X of oxygen times P total. Substituting the value, we have P of oxygen equals 0.250 times 6.00 atmospheres, which is equal to 4.50 atmosphere. To check if the answers are correct, the sum of the partial pressures of all components must be equal to the total pressure, where 1.50 plus 4.50 is equal to 6 atmospheres. Therefore, the answers are correct. You did a great job. Now let's proceed to example number 4. A sample of air in a container was analyzed to contain 0.390 moles of nitrogen, 0.102 mole of oxygen, and 0.0085 moles of other gases. What are the partial pressures of these gases in the container? If the total pressure is 750 milliliters of mercury, given values are the amount of nitrogen, where it is 0.390 moles, an amount of oxygen of 0.102 moles, and amount of other gases 0.0085 moles, and a total pressure of 754 millimeters of mercury. The goal in this problem is to get the partial pressure of nitrogen, oxygen, and other gases. First step. Calculate the total number of moles. Total moles is equal to moles of nitrogen plus moles of oxygen plus moles of other gases. Substituting the values, where N total is equal to 0.390 moles plus 0.102 moles plus 0.0085 moles, which is equal to 0.5005 moles or 0.501 moles. Just take note that significant figures is up to 3 decimal places based on the given values, but we will use the value of 0.5005 moles in the next step of the calculation to minimize errors. Second step. Get the mole fraction of each gas by dividing the number of mole of each gas by the total number of moles. For nitrogen, we have X of nitrogen is equal to 0.390 moles over 0.5005 moles, which is equal to 0.7792. For oxygen, X of oxygen is equal to 0.102 moles over 0.5005 moles, which is equal to 0.2038. For the other gases, X of others is equal to 0.0085 moles over 0.5005 moles, which is equal to 0.0170. Again, we will consider rules on significant figures on the final step of calculation. To check if the answers are correct, get the sum of the mole fraction. We have 0.7792 plus 0.2038 plus 0.0170 equal to 1. Therefore, the answers are correct. Last step. Calculate the partial pressure of each gas from the mole fraction and total pressure. The partial pressure equals mole fraction times total pressure. For nitrogen, where P of nitrogen is equal to 0.7792 times 754 millimeters of mercury, which is equal to 558 millimeters of mercury. For oxygen, we have P of oxygen is equal to 0.2038 times 750 millimeters of mercury, which is equal to 154 millimeters of mercury. For other gases, P of other gases is equal to 0.0170 times 750 millimeters of mercury, which is equal to 13 millimeters of mercury. A way to check if the answers are correct: get the sum of the partial pressure of all components and must equal to the total pressure, where 588 plus 154 plus 13 equals to 754 millimeters of mercury. Therefore, our answers are correct. To summarize, Dalton's law of partial pressure states that the pressure of a gaseous mixture equals the sum of the pressures of each component as if it were alone. The ratio of the partial pressure of a component to the total pressure is just equal to the mole fraction in the mixture. We have here our references or bibliography for further readings. Thank you.